Log on, tune in, find out. Another good idea from Cambridge.
You want me to? You do it. You're going to do it, but you didn't shut.
Sorry, I was talking to you. Sorry, it's organised. So it's a great pleasure to have Neil Copland here, who's from Quest?
Sequest.
Sequest in Sogang University in Korea.
Yeah. Okay, thank you very much. So today I'm going to talk about double sigma models and double field theory. A very vague overview of the idea here is we all know T-duality is a very important property of strings that doesn't exist for point particles. We need the winding of the strings round a compact dimension. So string theory on a circle of radius r is equivalent to a circle. String theory on a circle of radius 1 over r. And of course it should probably be an alpha primed on the top there to get the dimension right. So quantized momentum modes are exchanged with the winding modes under this T-duality. And if we split the string coordinate into left and right moving pieces, then the T-duality changes the sign of the right moving part, but not the left moving. So if we define a dual coordinate x tilde by the left moving part minus the right moving part, then the T-duality will interchange x and x tilde. So this is for one compact circular dimension of constant radius. But if we have a d-dimensional torus, then the T-duality group is enlarged to ODD. So there have been many attempts over the years to make this ODD symmetry into a manifest symmetry of the action. And this usually involves doubling the coordinates so that these additional dual coordinates of this form are used in addition to the ordinary coordinates. And there's always some complication that some price has to be paid for this doubling. So what we're going to try and do here is connect the field theory, effective field theory double picture and a picture with the double, a sigma model for the string world sheet with a double target space. So here's the vague outline. So start by talking about the double formalism, which is going to be an example of one of these doubled sigma models. Talk about the constraint, which is in some sense the price we pay in this situation for doubling the coordinates, and how we can integrate this constraint into the action. And then talk about the background field method, which is how we normally obtain the string, the beta function for the string sigma model. And then we'll switch a bit onto field theory and talk about double field theory and the generalized Ricci tensor, which occurs here. And then we're going to look at the connection between the two. On a flatbird background, I'll explain what I mean by that here, but this is basically what this double formalism is defined on. And then finally we'll talk about a more general double sigma model, which doesn't have the restrictions to a fibered background that we have here. Okay, so we're looking for a duality invariant picture, and we want to introduce this ODD invariance and look for what kind of new structures can emerge when we start speaking in terms of this ODD. It's a more unified picture of the massless NS modes of the string, the NSNS, the metric, the B-field antisymmetric Kalbermon tensor, and the dilaton. So in some sense they're treated more equally, and we have some double geometry, which is not just the geometry of G, but also of the antisymmetric tensor and the dilaton as well. And this part of the motivation for this kind of formalism is that it could allow you to have a geometric description of certain kinds of string backgrounds, such as T-folds. So T-folds, it's a similar idea to an ordinary manifold, where you have different patches, and in the patches you can divide it locally as well, in patches you can patch together with diffeomorphisms or gauge transforms, and here we can generalize the transition functions to also include t-dualities, and look at the possibility of getting new compactifications, and also just these t-folds, which in the ordinary undoubled string language are no longer geometric because we have these t-duality transition functions. In the doubled picture, they become geometric. So this double field theory, originally part of the motivation came also from string field theory, where you expect that the vertex operators in closed string field theory should also depend generally on this x tilde coordinate in these toroidal backgrounds. So in some sense it should also be not just, well, truly doubled theories should depend on these x tilde coordinates independently of the x coordinates as well. But we'll see we normally have to restrict away from that case. So let me start with the double formalism then. So it's a sigma model describing a torus fibration in which the fiber coordinates are doubles, but the base coordinates are not. So we'll just use this x here to describe some d ordinary coordinates and d dual coordinates, exactly as I showed on the first slide. So the formulas I'm going to use is due to Hull, but there was lots of earlier work on double sigma models by people like Saitlin, McNaran and Schwartz, Sen and Duff as well. And the very simplest form of this Lagrangian we can write down looks like this. We have looks like an ordinary kinetic term for the doubled coordinates now. And instead of just the metric, we have some double metric, which is indices which run over the complete doubled set here. And this Ly is just Lagrangian, ordinary sigma model Lagrangian for the base piece. So this generalized metric,
Non-compact.
sorry?
Non-compact.
Sorry?
What's y?
Y is the base coordinate. So we just make some split into fiber and base. We only double the fiber piece.
It's like the compact. Doing some
Yeah. So, but the point is this h is only a function of the base coordinates, the y's. So here is how h is described in terms of the h. Well, this small h here is just the metric on the fiber to differentiate it from the metric on the base, and b is a symmetric tensor. And this is a form which is familiar from various situations where this ODD symmetry crops up, such as generalized geometry and just compactifications of supergravities down to lower dimensions can also appear where you have this ODD symmetry appears. And we also have another metric in the game, which is this just the ODD invariant metric. And this h is a form that if you raise the indices of h with L, then you get its inverse. And in fact, h is the most general symmetric. Yeah.
All right. You say it's another metric, but shouldn't I think of it as like the tangent space in some sense? I do normal geometry, I'd have a metric G, and I have Vierbein, and it relates to
No.
delta or whatever the metric is.
No. It's like a separate metric. I mean, later on we'll go to the tangent space, and there'll be tangent space forms of each of these. Okay, so this is actually the most general symmetric tensor that has this form. Okay, so constraint, point is we've doubled the degrees of freedom effectively here by adding an extra set of coordinates on the fiber. So in order to be consistent with what we started with, we need to half the degrees of freedom again, and this constraint does this. So first of all, we have to impose this constraint externally, and you see it's just written in terms of the world sheet Hodge dual and L and H, the two metrics we saw on the previous slide. So if we do integrate to tangent space and introduce a Vierbein, one can diagonalize both of them basically. And in that case, this constraint, you can see, takes a very simple form. For the first half of the coordinates, this is just self-duality, and for the other half, it's anti-self-duality. So this is a chirality constraint, and it basically says, well, double the coordinates, but half of the new coordinates are left moving and only, and half of them are right moving only. So if we do this explicitly in the simplest case, just the circle of constant radius r, then these combinations p and q of x and x tilde are the chiral combinations. Now we'd like to incorporate this constraint into the action in order so that we can perform the background field expansion later. We don't want to have to add this constraint externally. So this was done a few years ago now by myself with David and Dan Thompson. So first of all, if we go to the chiral frame that we showed on the previous slide, we can impose this chirality constraint a la PST. And you're probably more used to the PST method being used for the anti-self-dual free-form field strength on a brane, but it also applies to scalars and chiral scalars in 2 dimensions. So we take the P and Q, these chiral fields we had on the last here. So say P is annihilated by d minus, world sheet derivative, and Q by d plus. And we can just rewrite the action in terms of this. This is just a rewriting of the action that we started with. And now these one forms, curly P and Q, are vanishing because of the constraint. And we basically like to impose these with a Lagrange multiplier, but it's slightly more complicated than that, the PST method. We introduce this two closed one forms, U and V, and then some PST gauge symmetry, but we fix that by choosing these to be time-like. And in the end, what we get out is an action which looks like this in the chiral frame. And this is an action written down for chiral scalars many years before by Florianini and Jacques. And we can move back to the coordinates we started with. And again, this action was written down by Saitlin as well. And so this was just for one compact direction with constant radius, but we can generalize this to any background described by the double formalism. And so this action here goes to this. So you see we've lost Lorentz invariance, well, manifest Lorentz invariance for the world sheet. So we have a d1 d1 term with the H metric, and we have a d0 d1 term with L. Now if we look at the equation of motion for this, it's a total d1 derivative, and we can integrate that up, and then we get the constraint back again. And we can show also that the equations of motion are equivalent to the equations of motion from the ordinary signal model in this background. So now we'd like to perform the background field expansion to look at the quantum consistency of this and see if it matches up with the ordinary string picture as well. So at one loop for classical violin variance, to extend to quantum theory, the beta functional must vanish. And how we calculate this is by looking at a quantum fluctuation around a classical background. So this classical background, x obeys the equations of motion, classical equations of motion, and we have some fluctuation pi, and you could just plug that in and expand, but the point is this pi is not a proper vector, so we should rewrite in terms of this psi. So psi is taken as a tangent vector from x to x plus pi with length equal to the length of the geodesic. And we find that an expansion in psi is covariant. And this means we already, if we do the expansion, everything's automatically organized into proper covariant tensors. So this was due to Honerkamp originally, Alvarez, Gomez, Riemann and Muki, and we go on to actually use a method, thanks to Muki, an algorithmic method where we can work out the background field expansion by just applying this operator a certain number of times and dividing by n factorial. So for one loop we only need second order, so we apply this twice, and we can work out the rules for how this acts on things in the Lagrangian. If we have a psi, it just annihilates it and so on. And you can see if we have a d psi, which comes out from acting on a dx, then we get a Riemann tensor. And that's going to appear at second order terms like the Riemann tensor. Okay, second order result is quite complicated. But once we have that, what we want to do is write a simple kinetic term for the fluctuations, find the propagator, and then use that to contract all the fluctuations out. And this propagator looks like this in the chiral frame. So if we introduce the Villebye and go to the chiral frame, then we simply have a chiral scalar kinetic term in flat space, and we know the propagator for that. There are more complicated double contractions like this with world-sheet derivatives in them, but these can be worked out as well. So all we do is work out all the contractions, and here using these rules we also have to take this second order Lagrangian squared, so that's where these contractions come in as well. So here this delta naught, this is the ordinary divergent piece of the propagator, and we've also included here this theta, which is not divergent, but it's ambiguous, and basically if we look at the propagator and we performed a worldsheet while rescaling, then this would change delta naught and not theta, and if we performed worldsheet Lorentz transform, it would change theta and not delta naught. And so while looking at the coefficient of this delta naught is going to keep track of any Weil anomaly, this coefficient of theta will keep any track of any Lorentz global Lorentz anomaly, which we'd like to check for consistency. Since we've lost the manifest Lorentz invariance interaction, we'd like to keep track of that as well. So after much manipulation, the result comes down to something like this. So it just has the form of our term we started with in the Lagrangian, with some new tensor coefficient w, and this is the fiber part and this is the base part. So although I say base and fiber, we're treating basically a trivial vibration here. The idea is that you could use this more generally to look at backgrounds. And this is the form of w. You can see it's just some derivatives of the fiber metric, and g is the base metric, and this is the base connection, and so on. And if we look at the coefficient, this is the coefficient of delta naught. If we look at the coefficient of theta, looking for Lorentz invariance, then it vanishes. So we know at one loop we still have Lorentz invariance. So we can regularize and renormalize this, and basically for the beta functional to vanish, w should vanish. And this is the equation. Yeah.
You've got t there. Is t time or just some dummy any dummy one?
For this t?
Yeah.
It's just an index. Sorry, dummy.
Same as AB.
Yeah. So, okay, so we can show that the vanishing of this is the same as the ordinary H and B beta functionals for the string in this setup. And this was work done a few years ago.
Is W a tensor?
Here's the one. Well, tensor, it's an ODD tensor, I think, on the fiber. Sorry, these.
Normally, in the undouble case, you have the real tensor, but
Right. So
the Ricci tensor.
So in the undoubled, in the ordinary case, this would be the Ricci tensor, would come out here, but this isn't the Ricci tensor of this metric H. So it really in this expansion here, I said everything's covariant in the expansion. It's covariant with respect to H, which is not really symmetry to expect. It's just a useful tool really to use that symmetry here. So the fact is that W is not equal to the Ricci tensor of H. And if we look at the base part, which is simpler, this R hat is the Ricci tensor of the base metric, and there's an additional piece involving the fiber metric comes into that as well. But that's an important, that's basically what the question is here, is what is this tensor in terms of ODD, and we'll talk about that a lot. Okay, so as I say, the ordinary case, this is the Ricci tensor, would be the beta functional for string sigma model, just in terms of G without the antisymmetric B, and that's the background field equation of the string. And so similarly, if you have an effective action just for G, then the equations of motion of that action are just Einstein's equation, and you can this is one of the ways you can see that the effective the background field equation, that the effective action of the string should be Einstein gravity, because this, well, one loop enough round, sorry, trio. So. Okay, and so what we're doing here is we know that the double formalism is equivalent to the ordinary string, and we do the background field expansion here on this arrow, and we get the vanishing of this W, and this paper a few years ago we showed that these are the same. So, and this W, it includes the antisymmetric tensor B. We can also include the dilaton in these kind of calculations as well. So in some sense here it's slightly simpler, because normally the more complicated part is when you include the antisymmetric tensor as well, and here it's automatically packaged up in some way. Okay, so I think that's what I said. So the point is, ordinary string background field equations, they come out of the background field expansion of this double formalism sigma model. Okay, so a bit of a change of tack here. Now we talk about double field theory. So I think you probably heard something about this last week as well. So double field theory is closed string field theory, inspired field theory, where fields depend on a double set of coordinates again. This was formulated by Alan Seeback and with of Holm as well later on. So we have the same fields again, HB and the dilaton, but importantly we need some kind of level matching constraint. So this comes from the string level matching, which says that this operator delta should annihilate all the fields. So this is just two derivatives contracted with the L metric that we saw earlier. And you can think of this as being saying like the momentum dotted with the winding should vanish. So originally the aim was to find a fully double theory in which the fields were general with only this constraint. But in fact, in order to make progress, we really have to restrict to the case where we have a stronger version of the constraint. Not only should this delta annihilate all the fields, it should also annihilate products of fields. And if we impose this constraint, it's pretty strong. It means we can always perform some ODD rotation to some ODD frame where the fields only depend on half of the coordinates. And we can choose these half the coordinates to be the original coordinates x. So you can write a background field a background independent action in terms of this E, which is the sum of H and B, and double dilaton, which is related to the ordinary dilaton by this relation. But this E transforms nonlinearly under ODD, and there's a complicated fashion under a new double gauge symmetry. But however, an action can be written down in terms of these, which has ODD invariance and a double gauge symmetry. However, things become a bit clearer when written in terms of the generalized metric. And we've seen this generalized metric before, because this is exactly what was used in the double formalism. In fact, the action can be written in an Einstein-Hilbert-like form for some gauge scalar, currently R here, where R is a function of H and the dilaton. So R is given in terms of this K, and this can be thought of as projector acting on K, and K is just given in terms of H and the dilaton. Okay, so a bit more about the double gauge symmetry. So this double gauge transformation can be thought of as some generalization of diffeomorphisms. If we look at how the generalized metric transforms under it, you see all the terms you would expect for a diffeomorphism, as well as additional terms which involve a contraction, two contractions with L. And this can also be described as a generalized Lie derivative. And these generalized Lie derivatives, they have an algebra, which instead of a Lie bracket, there's some double generalization of a Courant bracket appears. Okay, so the generalized metric and the Courant bracket, this is a double form of the Courant bracket. It's reminiscent of generalized geometry, of which with Gualtieri and Waldron and Brent have written similar, have written work which is quite related to this double field theory, but in a generalized geometry context. So we heard about that last week too. Okay, so we identified this this R tensor as a generalized Ricci tensor. So it's a function of the antisymmetric tensor and the dilaton as well as the metric. So if it's the analog of the Ricci tensor, then it's on some new ODD differential geometry. And there's been various approaches to understand this. So Barclay and John, who are in Sogang as well, works in terms of projector, just written in terms of the two metrics like this, and a semi-covariant derivative which annihilates all the basic fields, so it annihilates both metrics and D, and formulates the generalized Ricci tensor in form of these. And there are other approaches in terms of double wheel binds. So this goes back to the early work of Siegel, as well as Holman Quack's more recent work on that, and the connection to these other approaches as well. And then there's this generalized geometry approach of Waldron, which is quite interconnected. And there have been many extensions to this double field theory as well. So Holman Quack, as well as Barclay and John, have looked at adding fermions and supergravity. There's also branes, Bergschuff and Chioni and Albertson, friends, have done that as well. And then there's also quite a related M-theory approach where instead of metric and the antisymmetric tensor, you've got the metric and the C field. The same theory of generalized geometry of Berman, Perry and Godasgar. And the relation of this to the double geometry was shown by Thomson, which is one way where you can see how the RR fields, etc., fit into the doubled field theory, because they should come from the C field as well as the B field that we already have in this picture. So there's double tetrarotate, there's double Yang-Mills, double KK monopoles, and so on. So you can apply this to various things. So it's quite a versatile framework that seems to have wider applicability. Okay. So now we'd like to relate these two together. So the first issue is that the double field theory is more generally defined than the double formalism, because we don't have to restrict to this fibered background. And the double metric can depend on any of the fields. It doesn't just have to depend on some separate undoubled coordinates. So to connect these two, we must restrict the double field theory to a fibered background of the kind considered in the double formalism. So first of all, you have to split interface and fiber parts and rearrange the coordinates into block diagonal form. Then none of the fields must depend on the fiber coordinates, so no dependence on x. And undouble the base coordinate, so only dependence on the y's and not the y tildes. So there's no b on the base as well, and we have to define the correct semi-double dilaton, which takes into account only the doubling on the fiber. So this was the double field theory dilaton, double dilaton D, and this is the double dilaton in double formalism, and this is only the base metric that appears in here. So neither of these is the ordinary dilaton. Okay, so haven't talked about the dilaton too much so far, but we note that if we look at the generalized Ricci tensor, we can rewrite the terms involving the dilaton in two parts, so that if we substitute this in, there's the parts involving GDG and there's the parts involving psi here. The GDG parts can be written like this, and in the brackets here we just have the equation of motion of the double formalism. So in the background field expansion we can just add a term like this into the action, and then the leftover phi parts can be written in this form, and this is familiar as from the Fradkin-Satelin term. So this is a shift in the beta function by introducing a particular counter term, and that's the Fradkin-Satelin term for the dilaton. So if we just add a Fradkin-Satelin term for this dilaton here, then we can also include, we can also find all the dilaton parts of the generalized Ricci tensor as well. Okay, and so in this backgrounds, which is basically all the backgrounds on which the double formalism was defined, we find that this W tensor is equal, well, it's proportional to this generalized Ricci tensor. So the vanishing of one is the vanishing of the other, and this is saying that the background field expansion of the background field equation of the doubled formalism at one loop is the same as the generalized metric equation of motion coming from the double field theory. So this is just saying that the double field theory is like an effective field theory for the double formalism on this class of backgrounds. Now, this kind of had to happen because we've said before that both theories are equivalent to the undoubled equivalence. But the important thing is that this generalized Ricci tensor is the central object in relating them. So if we just consider the case of the ordinary string sigma model with only the metric G, what we would find here would be the ordinary Ricci tensor. So in the double picture, this is what seems to be playing the role of the Ricci tensor. And we reiterate again that it's not just the Ricci tensor constructed from this metric H. And this double Ricci tensor, it's not just a function of G, it also contains B and the dilaton packaged up in some ODD tensor. Okay, so how can this be interpreted in a more general double differential geometry? And I've mentioned various approaches to this topic by Holm and Quack, Lee, John and Park, and Waldron and all, which are very interrelated. Okay, so that was the case for the double formalism, but then we're led to ask if a more general sigma model exists, one for which the background field equation gives the whole double field theory, basically. So there are some difficulties in writing this down originally. That's why, well, the double formalism was restricted to this class of backgrounds with no dependence on the final coordinates. Well, what we find is if we just write down most simple generalization imaginable, so we just take the fiber part of the action we had before and allow h to depend on all the double coordinates, then this is exactly what we need. So general actions of this type were studied by Copland, but usually some restriction had to be made before we could go much further, either to constant h, or the case when a little bit was known about the case when h just depends on the original coordinates. And the restriction of this kind of sigma model to group manifolds was examined by a couple of groups as well. So here we have a dependence on x, but of course it's not completely general dependence on x, because if we want to get the double formalism out on the double field theory out on the other side, we should have the same freedom of x dependence as the double field theory. So x should obey a constraint, the level matching constraint. So we impose the strong level matching constraint in this case. Of course, this means we can always retreat to a frame where there is no dependence on the dual coordinates, and there things should be equivalent to the ordinary string sigma model. So we can always look at this frame in which there is no dependence on the dual coordinates. Okay, so as it's so strong, it means that the coordinate dependence of all the fields is only on an isotropic subspace of the doubled coordinates space. So even if the fields are evaluated at different world sheet points, the dependence on x is so restricted that this must hold still. Okay, so now when we try and integrate the equation of motion, we have this additional term on the right hand side, and we can integrate anyway, and we have some non-local term sitting on the right hand side like this. And so this is what stopped progress before, but the point is the strong constraint is actually just what we need to mean that this term never actually comes into play. So what we find is if we have the equation of motion, we need to substitute this somewhere in what we'll use later. Then this free index is always contracted with a raised derivative. And this means that we have a contraction of derivatives here, and the strong constraint means that must always vanish. So there'll be no contribution from this non-local term. And so often we can either use this argument or see it explicitly if we rotate to the canonical duality frame where nothing depends on the x tilde coordinates. Okay. So we can perform a few checks on this more general sigma model with the strong constraint. So first of all, we can check classical Lorentz invariance, and we need the strong constraint even to show at classical level that we have Lorentz invariance. So the condition for Lorentz invariance, we basically have the vanishing of the chirality constraint squared contracted with L. So we basically have the left-hand side squared contracted with L. Of course, we could substitute for the right-hand side, and basically you have something which vanishes by the strong constraint. Or you can see that very easily in the canonical duality frame, where you can see that you will have a d tilde derivative on one of the terms, and because nothing depends on d tilde there, then it has to vanish. You can check equivalence of the equations of motions with the ordinary string sigma model. Again, we need to use the strong constraint. Both cases, it relies on being able to integrate half of the components of the equation of motion. and we only need to be able to integrate those half. If we come to look at the double gauge transformations in the sigma model, well, we know that H and L transform properly as ODD tensors, so we need to check that first of all, that D1x transforms properly. Now we know how the x's transform, and we can get the transformation of D1x tilde from the equation of motion. These are the half of the components we can integrate are for the D1x tildes. And we plug everything in, and we see that we have the right transformation for this to be a double gauge vector. And so the H D1x term has double gauge invariance. However, the L term, we can't do that because we can't integrate the half of the components of the equation of motion to give us d0 x tilde. Could try adding total derivative to get rid of them. And the new term has the correct gauge transformation, but of course there's a transport term, and the difference of the transport term from the new term from the original is not a total derivative, which means that what really is invariant is the term once we've added the total derivative. We can't then take it away again. But in fact, this is actually familiar from the double formalism. In the original papers of Hull, and also in a later paper where myself and David looked at the partition function, what you find is you need this topological term. So this term is the total derivative. This is just some constant matrix omega. So once we add that, then we can see that we have double gauge invariance. Problem is this is not manifestly ODD invariant. We can work out what the term should be just by applying ODD rotations to it, and we'd rather have ODD invariance. But this is just needed to show this double gauge symmetry. It's not needed in what follows in the background field expansion. It doesn't play any role in that. Okay, so if we perform the background field expansion exactly as before, again we have to use this half the components of the equation of motion that we can integrate. And what we find is that, well, first of all, the Lorentz anomaly, so this is terms proportional to theta again, vanishes at one loop. So although we don't have manifest Lorentz invariance on the world sheet, we still have this Lorentz symmetry at one loop. We can include the dilaton terms as before, and they also vanish on shell after use of the equation of motion. And the final result we get is that the background field equation of this sigma model with the strong constraint is exactly the generalized Ricci tensor familiar from double field theory. So this is basically saying double field theory with the strong constraint is like an effective field theory for the more general sigma model. Okay, so that was the result of the last paper, but that leads to some other questions which were really motivation for doing this in the first place. So the double field theory is an effective field theory for this sigma model. It's basically the one loop calculation, so we can do the two loop calculation to try and find the higher order corrections to double field theory. So I know Olaf Holm and Zubach have been looking recently at possible higher corrections, and the picture is not clear. You know, what a Riemann tensor squared term should look like for the double field theory. It seems it's not, there isn't one. So part of the problem is at higher order, we probably expect this invariant, this generalized metric to have alpha prime corrections. See the work of Meissner. So this picture is not clear what the next order of double field theory should be, and people have been trying to write down this next order terms for a while, and it's not clear. So using this, just basically doing this two-loop calculation for this model, it should drop out. And this two-loop calculation, well, of course two-loop calculations are pretty horrible, but what makes the ordinary string case most horrible is having to deal with the antisymmetric tensor as well. In this case, it's automatically included in the symmetric H, but of course there's a price we have to pay. So we know the fact that we no longer have Lorentz invariance on the world sheet complicates things slightly. But okay, this calculation is underway. Okay. So another point is, I mentioned earlier how when we did the background field expansion, the point of these coordinates psi was so that the objects in the expansion were tensors. Now, what were the tensors under? They weren't tensors under these generalized diffeomorphisms. They were tensors under just diffeomorphisms of the doubled space. But really, for some truly powerful way of doing this expansion, we should find the correct derivative in order to do the expansion in, which is suited to this double geometry. So in that case, so the fact is actually here the background field expansion, choosing the Riemann normal coordinates doesn't actually help us very much, because yeah.
What do you mean by Riemann normal coordinates for the double thing? Because I don't really know what I mean by connection.
Exactly. So, well, if you go back to the ordinary case, right, you have some concept of a geodesic and
Yeah, I'm
so on
happy
and
with
so
a
on.
geodesic normally.
Yep.
I'm not even sure what a geodesic is in double geometry.
Right. So what we've been doing here is actually just expanding around a geodesic in the two-dimensional space with metric H. So that's not really the.
You're saying take the usual geodesic equation for the metric H.
Yeah, it's just the ordinary geodesic equation. So that's why it's not so simple. It's actually still quite a mess. So if we could find the equivalent of the geodesic equation for the double geometry, then things should be much simpler. So, for example, the point of this expansion is you get covariant derivatives acting on G in the ordinary case, which simplifies everything because it vanishes. But here we have covariant derivatives acting on L as well, which doesn't vanish. So I mentioned earlier how, like in this Park, John and Lee picture, they defined generalized covariant derivative, and that annihilates G and L, H and L. So if you could find geodesics of this and so on, then the expansion should be much simpler, and I think that would be really powerful. But of course, this is the whole question of what are the connections on this double space and so on. So I have started trying to look at this as well, and I have kind of geodesic-like equation, but that's early stage, and I'm not quite sure on the interpretation. So. Okay, so that's another question for the future. One more. So in the double formalism, we started from Lorentz invariant Lagrangian plus a constraint, and we did the PSD procedure to get the Lagrangian that we used for the background field expansion. This generalized picture, we're starting from this point after the PSD procedure. What would be the original Lagrangian, and what would be the constraint, more importantly, because it seems the constraint it's only there for half of the components. So how could that be written in some ODD invariant way? It's not clear. And then another question is, how can we generalize away? Is it possible to generalize away from the strong constraint? I don't know. One possible angle there is these group manifold approaches earlier, where you have some kind of structure, which is not the strong constraint, but which some kind of structure which enables you to still work. But that's just an idea to look at. Okay, so just to conclude, the double formalism provides a t-duality symmetric sigma model for a certain class of fiber backgrounds, and it aims to make non-geometric backgrounds such as t-folds geometric. On the other hand, we have double field theory, which describe a truly double field theory, but is restricted to the strong constraint, to the generalized metric formation. But it brings new double geometric structures to the fore. We have some kind of generalized notion of the Ricci tensor, and we'd like to understand the full doubled differential geometry of that. If we restrict double field theory to the kind of background that the double formalism applies to, these sort of trivially fiber backgrounds, so the generalization to proper fiber backgrounds should be civil. Then we find the equation of motion of the former is the background field equation of the latter, and we can go further and work in this more general sigma model where the metric is allowed to depend on all the double directions, and it gives the full equation of motion of the double field theory as the background field equation. Okay, thank you very much.
Any more questions?
Maybe you said this already, but if you consider the sigma model with the depending on the double coordinates, is there not a double conformal anomaly in that? I mean, conformal anomaly usually counts the number of dimensions.
I think that the point is that because rather than bosonic directions, we have chiral bosons, each only contributes half.
So I see. So it's separately left and right conformal.
Well.
More?
So, do you think you will be able to write out curvature square terms as coming from double geometry?
I'm not sure. It's complicated. I mean, I think we should be able to see what the two-loop contribution is, but then if you have to correct the metric and maybe the transformations as well at the next order, then it's not well.
Well, you know the ODD transformations themselves don't get corrected.
Yeah.
So you wouldn't expect that.
Yeah.
But I guess, as you said, the metric
Uh-huh.
can be done.
Yeah. Well, I mean, we think it'll work, obviously.
But you'll get, I mean, if you do the two-loop computation, you're going to get something.
Yeah.
Right.
If the computation works. Well, there are some aspects of it which are a bit more complicated, like the regularization. At two-loop, it gets more complicated, and because we don't have Lorentz invariant orbit here, it's not so clear what the proper IR regularization should be.
Have you checked Lorentz invariance at two loops?
No, it's still, we're still checking
Yeah,
out
it
the
sounds
first
like
part. So,
How
but
do you
we will.
regularize?
Yeah, so we're just using dimensional regularization.
Isn't that going to cause all kinds of problems if you can't?
Yeah, probably. So,
I mean, you can use dimensional regularization for the sort of non-chiral case, and it's probably not a problem, but anything chiral is going to be a chiral issue.
yeah, I mean, we're definitely looking into that.
If you take the Florini-Jakiv action, I think you can dimensionally regularize that.
Certainly okay.
Even on the ordinary bosonic sigma model with a B field, you have to worry about the fact that
opposed to an epsilon you knew in there. It doesn't generalize
Mhm.
to, and there are ways of doing this, but it introduces evanescent operators, which things which vanish when you go to 2 dimensions, but it makes life complicated. Maybe they don't really, not important that 2 is too much, but I mean, you've got subdivergences which you need to worry about.
Mhm. Yeah, I think there's a series of papers by Son and Shine on regularization in these chiral models, which I think Dan's looking into, but yeah, we expect some trouble. No,
Any other questions? Let's thank Neil again for that talk.